Welcome to our second video in which we'll be learning about the equation of a plane. Well, we've already revised the equation of a straight line in 3 dimensions, and here are the equations we looked at, and here are the ones we're going to learn today. What I showed you in the previous video was, for a line, we have a general point R, a fixed point on the line, which we call A, and the direction of the line given by the vector B, and lambda is a parameter which is a real number. So, looking to the equation of a plane, it doesn't take too much imagination to think R is the general point on the plane, A is still a fixed point, and because a plane is 2 dimensions, we have 2 direction vectors, B and C. The other equations here we'll look at later on. So this is the task. We have a plane called pi. Often in exams they use pi or pi1, pi2 to denote a plane. We have R, which is some general point on the plane. We have A, which is a fixed point. And in this example we have other points B and C which are in the plane. Therefore, if we connect A to B with a vector called small b, it will be parallel to the plane. And if we connect A to C with a vector small c, it will also be parallel to the plane. So the question is, how do we get the position vector here of R, which I should have put a small r there actually, this R, how do we get the position vector of any point in the plane from these 3 vectors A, B, C? And it's pretty simple to do that. We can think, well, if we consider in this diagram approximately a third of vector B and approximately 3/5 of vector C, and then try to use them to arrive at point R. Good old copy and paste there. I hope you can see that the position vector of R is the resultant of OA plus AM plus MR, shown here. And you can do that for any point in the plane. You could even think of a normal XY plane which has an x-axis and a y-axis. Think about it, those are 2 different directions, the x-axis and the y-axis, and they define every single point in the plane. In the same way, every single point in the plane pi is defined by a b-axis and a c-axis. It's just that to get to any point in the plane, we have to get onto the plane first with the fixed point. So, that's the vector equation of a plane. So, to see an example, which is on the handout, it starts with 3 points A, B, C, and then to find the directions, you have to find the vector AB, I'll let you work that out and confirm that you get this. And the vector AC, similarly, work it out. And then fixed point A. And then you replace them in the general equation and you get this. Actually, we could have started with point C as the fixed point. It amounts to the same thing. So that's the vector equation. The parametric form isn't actually mentioned in the syllabus, but here's how it goes. Once we have the vector form, just like we did with straight lines, you basically remove the brackets and multiply things through, and you get this system of equations for the parametric form. Now, the Cartesian form, of course, means there is no mention of the parameters lambda or mu, and that involves eliminating them from the system, which can be done as follows. Now, usually we don't have to do this at all. There's another method which I'll show you probably in the next video. A much quicker method than this. But that's the Cartesian form. And hence show that the vector whose components are the coefficients of the Cartesian equation is normal to the plane. Well, here's the Cartesian form. I'll let you finish this. 1, 3, 1 are the coefficients. I'll let you figure out what is the scalar product there and what that means about this question. And also see if you can figure this out. What is B cross C? You may find a relationship between B cross C and this equation. Okay.